Hello friends, welcome to Develop. In the last few videos of this series, we were seeing how this creative SBS A300 sound system works and was dissecting this circuit board, the driver board of the creative sound system. So here it was a TDA8510J, the driver IC, you can see. And we have already talked about this overall concept, and we have talked about the AC to DC conversion section and the on-off section. In today's video, we'll be looking at the signal detection, like what happens to the audio signal that enters into the audio system through this 3.5 millimeter audio pin, that signal detection. Then filtering happens, that low pass filter, that low frequency signals are allowed to go, and the very high frequency, the noise creating hissing sounds are removed by using MC4558 op amp. So you have a dual op amp system for both the channel, L channel and R channel. And next we have audio amplifier, that is based on TDA8510J. So that IC is actually having 4 amplifiers, 2 amplifiers dedicated to each of the audio channel, and rest of the 2 amplifiers are for the bass speaker. And you have bass booster section. So we'll see all these things in today's video, and we'll take a help of the circuit simulator. So here I have structured entire thing in a single file. We'll share the every circuit file link in the description section. So I didn't take the left channel and right channel. I have configured the simulation for only one channel. So we'll explain step by step what's happening from the signal detection. We all know the audio signal in the audio system is entered into the system by the 3.5 millimeter audio pin. Now the question is, what happens after that? So let's say this oscillatory signal source is that signal that is coming from some computer or maybe mobile phone and is getting entered into the audio system. Now it directly goes to the volume controller, which does nothing but varies the voltage. So that volume controller is a potentiometer, so where you can adjust the effective voltage by changing the resistance. Okay, so that's what potentiometer does. So you are changing the sensing voltage using this potentiometer, so that impacts the downstream circuit or the voltage supply quantity, and that indirectly impacts on the audio or the volume of the system. Now voltage from this pin creates a closed loop of resistor and capacitor, and finally that voltage is detected from here. Now it goes to a capacitor. From capacitor it goes to this NPN transistor. Now these are Q1 and Q2 transistor. So if we just go into that, yeah, that Q1 and Q2 transistor you can locate here. So you see here is the Q2 transistor and here is the Q1 transistor. So just next to that volume controller you have these things. Okay, and these are the signal detection capacitors. Okay, so Q1 Q2 transistor from this transistor. So these are NPN type transistors. So the basic concept of NPN transistor is like, if this is a base and this is the emitter side and this is the collector side. So if you maintain around 0.7 voltage higher than this emitter side, what I mean to say is, if VB is greater than VE, and that too by a value of 0.7 volt, so a small amount of current will flow in this direction. Now based on the beta value of the biasing and the condition of this PNP, so a large amount of current will flow in this direction. So what this circuit is doing here, so one signal voltage is coming here and is getting fed to this base point, and base point is properly biased by taking voltage. So I talked about the voltage source earlier. Here I have considered only 10 volt single voltage as a voltage source. So that 10 volt voltage is divided by 100 kilo ohm resistor here. So effectively it's giving a voltage of 5 volt here, because if you just go to the voltage division rule, it becomes 5 volt here. Now here is a 5 volt. Now if you see this 5 volt and the voltage coming from here, this voltage is a very tiny volt. So this is going to be somewhere around 400 millivolt kind of number. Okay, not even a single volt. Now the question comes, how this 400 millivolt impacts this 5 volt. Here comes the role of this capacitor. It's very important, and it literally took some time to understand for me. So when, let's say, this voltage is 0 and this is 5 volt, so there is a delta of 5 volt between this capacitor plate, this polarized capacitor. Now when some voltage comes in this terminal, like 400 millivolt, so the capacitor tries to push this voltage up so that the delta V, that is 5 volt, remains. So when this voltage is 400 millivolt, so eventually this voltage will try to become like 5.4 volt. So that way this transistor detects the voltage signal, audio voltage signal. Now one question comes, so why this signal detection is required? Why we can't take this voltage directly to the downstream useful circuit? So the problem is, so that system records some kind of ampere, some small current, or maybe the voltage requirement is high. The problem here with the audio supply from 3.5 pin is, if you draw a significantly higher amount of current from that pin, so that audio card of your PC or mobile phone will create audio distortion. So this system is not designed to draw amp. Okay, so this will not be able to give you good amount of amp even to operate the circuit. So for that you need a buffer zone. So this is that buffer zone, is the audio signal detection using a NPN transistor. Okay, so this small voltage variation is causing a small current here, base to emitter current, and that small current is creating relatively large amount of current in between collector to emitter. Now that large current, when it is flowing in this direction, so this is going to give a delta V here, voltage difference. That voltage difference is sensed by this resistor, this 80 ohm resistor. So let's see in simulation how it's working. So I've just started the simulation. Yeah, see here this blue line indicates the audio signal in, which is varying around 0 volt. So you can see the range of this volt is 500 millivolt. So what this transistor is doing, it is clipping this voltage to a higher value, plus it is creating a buffer between this audio signal source and the downstream audio amplifier, filter, etc. So the necessary amp, whatever is required, it is drawn through this route, okay, from the actual power supply source. Now if you see the amp value, things will be a little bit clear. Yeah. Now you can see what's the order of amp in this loop, means how much amp is getting drawn from the audio pin, audio source. It's negligible. You see, some microampere, 9.62 microampere amount of current is getting drawn. And see here, how much is the current flow through this transistor, flowing through the transistor, and the same thing is flowing through this resistor, major portion. Okay, so that amount is 1.77 milliamp, significantly higher than this 9 microamp. Now how much current is actually drawing? See, now you see the downstream circuit is not drawing that much of current, but that orange line, but that drawn current is relatively higher than the audio pin supplied ampere. So you see here it was around 9.62 from audio pin, and the circuit is drawing somewhere around 72.9 microampere. Okay, so in this specific case it's drawing somewhere around 8 times. So that extra amount of current is getting supplied by the actual power supply, not the audio pin. Okay, so that prevents the audio distortion. So that's the key role of this section. Now if you go by theory, the single NPN transistor also can be used as audio amplifier. So why we are not using it? Actually this PNP transistor and this configuration is called class A amplifier. Yeah, so there was a time when only this amount of things, this NPN transistor can, or a single transistor could be used as a audio amplifier. The problem is power consumption is very high, so the efficiency is very low. I think it's somewhere around 50 to 60% power efficiency this kind of a transistor can give. Plus you didn't do any kind of a like audio processing, etc. So if you do the amplifying of the signal before that, so there will be lots of noise, etc. So the main reason is the efficiency of this transistor. Why the efficiency is so low? The reason is, in this audio signal cycle, so you have to keep the base sufficiently high so that negative cycle and positive cycle, in both the cycle, it's giving current flow. You see here, so effectively in the entire cycle this is on, and I can show you if there is no audio signal. Let's say, okay, let me open this audio signal supply. Even in that case there will be a current flow through this transistor. Let me show you. To demonstrate you that that there is no audio signal, I have attached a switch here in the audio loop, audio pin loop, audio signal loop. So if you see that this audio signal is not getting supplied, and even in that case, that transistor is passing some amount of current to the ground. Okay, so if you just right now ignore this part, the right side flow. If you concentrate here, this current is flowing through even though there is no audio signal coming in. So of course, if the audio signal is coming in, so some current is going to flow here. So I think it's better I remove this thing. Okay, you see here, so I have attached a switch here. So the switch is connected, means audio signal is coming, so some current flow is there. Now if we just remove that switch, even in that case also some large amount of current flow is there. So that large current flow is going to cause the inefficiency in the circuit board, the power inefficiency. Okay, now let's move to the next section, which is a low pass filter. Let's first understand what's a pass filter is. So the classic pass filters are prepared using the resistor and capacitor. Low pass means it will allow to pass low frequency signal but will not allow to pass high frequency signal. So it will ground the high frequency signal. So let's see how it does in a classic way. So you have a capacitor here, you have a resistor here, this is V in, this point, and you have a V out here. So what happens? So you can, in audio system, you can give different frequency voltage here. So let's say like this. So this kind of thing or this kind of thing. Okay, so different frequencies. So this is like low frequency, this is high frequency audio sound. Now here in the low pass filter, what you want, that you want to ground all the low frequency. You don't want the low frequency sound to come into your speaker, so it is going to create some hissing sound, bad sound kind of thing. So you want to remove that. So if you could use that resistor capacitor based low pass filter, what would happen, like the low frequency sounds will pass through the circuit, and from V in will go to V out, and the high frequency sound, the major portion will be getting grounded. Now this is happening because of the property that the resistance of a capacitor that reduces when the frequency increases. So using that concept, this kind of circuit can be done. Now based on that, you can get a cutoff frequency which is 1 by 2 pi RC, this formula. So this will show you at what frequency, till what frequency it is going to allow, and beyond what frequency it is not going to allow. Now if we plot the things, so it is like this is how the gain is getting impacted. So here you have a frequency, and so since it's a low pass filter, so it will not allow some frequency to come at the downstream. Downstream means this side, from this side to this side. So this side is a gain. This is often represented by dB, which is log of a amplitude of output by amplitude of input kind of thing. But you can think that after a certain frequency fc, the signal gain is reduced by the circuit. Okay, so whatever before this critical frequency is retained, it may be boosted also. So there are scenario, but just keep it simple. So here the gain is 1, so it will allow to pass the signal till this fc. But in fc, as the frequency increases for the signal, so it will reduce that gain. Means so if here you have a large amount of a very high frequency, like intense guitar sound or some hissing noise sound kind of thing, so those things will be grounded, and here we will be getting crystal clear sound with the frequency having of this zone only, maybe some amount of here also. Okay, so that's about the low pass filter. Means it's going to allow the low frequency to allow, but not allowing the high frequency. So that's what is low pass filter. And of course the opposite is the high pass filter, where the circuit allows to pass the high frequency sound and prevents the low frequency sound. Okay, so the same thing here is done by a op-amp circuit, and the op-amp is used here because just using some component, a very small number of component, a second order low pass filter can be created using op-amp and capacitor. Okay, just pay attention here, the key component here, you have the actual op-amp. Now some of you who doesn't have idea what an op-amp does, so The operation of an op-amp can be understood using very simple. So this is non-inverting and this is inverting. So let's say this is A, B, and here you have C. So this is what this op-amp is. Now this, see, non-inverting is the plus, inverting is the minus. So what this op-amp will try everything to keep this voltage at A and B at the same value. Okay, now if there is no feedback, like no signal coming from here to here, so if there is no feedback, no signal going back, in that case, if this A by B is A minus B, so this minus actually is represented here. So that's why this is inverting signal. If this A minus B is greater than 0, this C will max up based on what voltage this is getting powered. Okay, C will max up to this VCC plus, and if A minus B is less than 0, so it will go to the minimum possible value, which is the negative power supplied to the op amp. Okay, so this was about no feedback, but if you give some feedback, things will change, and there are so many different combinations of op amp applications are there using this feedback. Now if you give a feedback, even in that case also the op amp will try to match this A B. So its objective is actually to make A minus B equal to 0 or A equal to B. Now the op amp will change the C voltage to do, it will try to do everything so that this A equal to B things is established. So here this op amp will do the same thing, and the eventual result of this op amp's activity is a second order low pass filter. Now why second order low pass filter? Now second order low pass filter can be assumed as a two first order low pass filter. The low pass filter that I've shown you with a resistor and capacitor, that was a first order low pass filter. So putting two low pass filter is equivalent to a second order low pass filter. Now to prevent the interaction between two low pass filter, so you need an op amp in between to prevent the interaction between the low pass filters. Now it's a very clever way. In this clever way, this only using one op amp and some capacitor and resistor, a second order low pass filter can be constructed. Now the second order low pass filter gives one advantage. So let's say this was the first order low pass filter. So this was kind of my critical crossover frequency, after which the frequency, so this was the frequency axis and this was the gain axis. So after which the gain is going to go low, or in other way, the circuit is not allowing those frequencies to pass forward. This was if this is the first order low pass, let's say first order low pass filter, the second order low pass filter will be like this. So its cutting is going to be very sharp, or at least as compared to the first order. So of course you can understand, so this is going to work better as compared to the first order low pass filter, because it will be chopping off the high frequency in a faster way as compared to the first order. Okay, so that's what this second order low pass filter using this op amp is doing. Now if to locate these things into the circuit, you should go, you see here, yeah, this black one. Okay, this IC is that op amp. Actually it's not a single op amp. This IC housing two op amp for the left channel and the right channel. Let me show you other view. Yeah, here you can see the thing in a better way. This one I'm talking about. This, you see, 8-pin IC. So let me open the data sheet for you. Yeah, see, this is the data sheet of that MC4558 op amp IC. See the depiction here. So that IC contains two op amp. So this is the inverting input, non-inverting input, and the output. So these are the A, B, C I was talking about, and this is the other one. So these two op amps are used for the left channel and the right channel of the audio system. And you see here the VCC plus and VCC minus. Okay, so this VCC plus and VCC minus, this is the positive and negative power supply for the op amps. This VCC is actually grounded here, and the VCC, it takes the required power supply from that power source or voltage source. Okay, so this IC is nothing but only two op amp. Now just if someone of you are interested, this op amp actually can be created using large number of PNP and NPN transistor, resistor, capacitor. So eventually inside that op amp also you have a transistors only. Okay, so that that calculation, that formula, if a minus b is less than 0, then do this, if a minus b is greater than 0, then do this. So that kind of things are getting done inside that op-amp just using transistors. Now once that low pass filter part is done, let's move to the most important part of the circuit, which is the class B amplifier. Now this class B amplifier, you see, it contains one op-amp, one NPN transistor and another PNP transistor. Okay, this is the power supply source of the speakers, the tweeter speaker, 8 ohm speakers. Okay, so this entire thing is housed inside the audio IC. Okay, this one, TDI8510J. So let me show you in actual this one, TDI8510J. This thing contains 4 number of audio amplifier. Okay, in audio amplifier, it's actually amplifying the ampere, not the voltage, ampere. So that's the important point to remember. So let's see how this IC is working step by step. The pin number and count etc. can be understood from the data sheet of this TDI8510J. So here you have a lot many things, but things are pretty simple, believe me. So, and this diagram gives a very good idea how the things are working. You see here you have an inverting input 1, inverting input 2. These are nothing but these two are your left channel and right channel signal input after the filter. Okay, and so something happens here and then it goes to that power stage. So don't go by this notation. Okay, so power stage, that is some transistors are there. Now once the powering is done, this output one is so left channel signal goes to the left speaker, right channel signal goes to the right speaker. That's one two set of audio amplification, and the balance 2 set of audio amplification is for your subwoofer. Okay, now for subwoofer, this voltage is these two input inverting and non-inverting, these voltages are detected from this audio signal itself. I'll show you this. Okay, so I'll show you how that is happening. So effectively this IC is predominantly for power amplification section, and let's understand only one power amplification, I think. So it's 4 times of that power amplification only. Let's understand. And these amplifiers are the class B amplifier. So earlier we talked about the class A amplifier using only one PNP or NPN type transistor. Here we're talking about the class B amplifier. The benefit of this class B amplifiers are it gives a superior efficiency along with the performance. Here I have connected some switches to demonstrate you some of the cases. So just to mark the boundary what we are talking about. So this is the class B amplifier domain. Okay, this is the part. Okay, so this is the part for class B amplifier. Here you have this 8 ohm resistor to mimic your speaker. Okay, that left or right channel speaker here, and here you have a large size capacitor to drive your speaker. So I'll show you that capacitor also. Here you see these are the capacitors. These capacitors are in series with the speaker itself. Now let's see how this audio amplifier is working. So here this point is a signal from the audio filter, that low pass filter, to remove the hissing sound. This signal enters into that TDA8510J IC, one channel. So when the voltage is high, means is significantly different from the base or inverting point, so this point also goes high. See here, now that high is very high because of that nature of the op-amp. So I told you that if A minus B is even greater than 0, it's going to go to the high value, very high value. So from there, this op-amp is showing you that very high jump in the voltage, this green line. Okay, that's the nature of the op-amp. Now there are a few other things is happening here. So one interesting thing is that when this is high, this is allowing this NPN transistor to flow current through this circuit. Okay, and means the positive cycle of this audio signal, so this is going to go active. In the negative cycle of this signal, this is going to go close. Okay, because the base voltage is going to go low compared to the emitter. So as I told you, we need to maintain some 0.7 voltage higher compared to the emitter. So this is going to close and that time when this is going to go low, that time this PNP transistor is going to go active. So in the negative cycle this is going to go active, in the positive cycle this is active. So alternatively they are taking charge and will allow flow of current through the circuit in the way the animation is showing. Now there is a catch. So See here what is happening. So this is the raw op amp only, there is no feedback. Okay, so there is no feedback from the base of the transistor, you see, and there is no feedback from the this collector emitter side of the transistors also. You see, the as expected, the op amp output is going to go to the max value, the 10 volt. Okay, and it's coming 0 and going 10. So that's not what we are looking for. This is the audio signal, and this is just max min kind of thing now. So in classic class B audio amplifier, what is done, so you give a feedback loop from this base of this dual transistor through a resistor to the inverting point. So what it will do, see here, now that feedback is tracking this voltage. So once this switch is closed, this voltage, that base voltage, is working as a feedback to that op amp. Yeah, so this is that interesting thing that I just wanted to show you. So this feedback is doing a very well job. You see the green lines. Okay, so the green lines are very good. Okay, so it's tracking the base voltage in a nice way, and it's following this audio signal, the supply in audio signal, in a beautiful way, and giving a voltage magnification. But you see here this distortion. Yeah, I'm talking about this distortion in the orange line. You see here, it's everywhere. Okay, this current flowing into the capacitor, in your speaker, is getting distorted. Some break is there. Now the reason of that break, that distortion in the current flow, is that because of that 0.7, that voltage, that excitation voltage required for the transistor. So what is happening here now, just to open this transistor for current flow, you need a higher than 0.7 voltage, higher than the emitter side. Okay, so your VB has to be greater than 0.7 plus your VE. At the same time here also, so here this is the emitter, here your VB has to be less than 0.7 plus VE. Okay, now to satisfy these things, so these two transistors are not going to allow current flow at the same time. Okay, so in one way you have a VE has to be greater than 0.7 plus VE, and another way you need a VB less than 0.7 plus VE. So 0.7 in plus 0.7, so you'll be having a zone of 1.4 volt or in this point, for which there will be no current flow between this transistor or this transistor. So this is what these zones are depicting. So this was the objective of mine, to put this switch and making this circuit. Otherwise this circuit doesn't exist in the board itself. Okay, now let me proceed how this problem is solved here in this IC. So here it's a very smart way. You have a feedback from the transistor output itself, this point. You see here, in a smart way, the feedback is taken from this point, which is the main current flow path for the transistors. Now from here you have a small resistors and then feedback to your inverting terminal. So what this this op amp will try to do, will do everything to maintain this voltage in such a way, will try to do everything, will change this voltage in such a way that this A voltage and this B voltages are equal. Okay, so because you have a feedback from here, so now the op amp indirectly knows what is happening here and will do everything here to change the voltage here. Okay, so directly will manipulate this voltage so that this voltage changes in such a way that A equal to B. So indirectly this op amp will try to minimize that distortion. Exactly, that's what is happening here. Let me show you. Yeah, now see in this orange line there is no distortion. Okay, yeah, I agree that there is some distortion in this green line, but you see your speaker is not here, your speaker is here. This 8 ohm is your speaker. Okay, so this audio amplifier is removing the distortion and it's giving a perfect current flow, smooth current flow here in this resistor. Now what has happened after doing all these things, if the voltage of this point of this voltage across the speaker is same as the voltage here in the op amp, so what we have amplified here, actually we have amplified the current. You see the large amount of the current flowing here. You see the current flow in this orange line, you have a 200 milliamp of current flow. In other area, let's see how much current we are actually drawing from the audio pin itself. Let's say we'll see this one. Okay, let's see how much current we're drawing. You see It's zero, literally zero. It's some microampere, 9.62 microampere we are drawing from the audio pin, and here we are generating some around 200 milliamp of current. Okay, so this value we are talking giving some random value of the resistor and capacitor, not so precise. Okay, can imagine what the things is happening here. Some microampere you're drawing from the audio pin and providing some 200 milliamp of current to the speaker. So that's the role of that audio amplifier. Now that's not the end, friends. So we have another section, that is the bass boosting section. Let's quickly see what's happening here. Yeah, in the bass booster section you have a Q3 transistor. So in the Q3 transistor, let's see what it is doing. It is taking the signal from the speaker root. You have the capacitor speaker, so the speaker is playing. From speaker root you have a resistor resistor in series and the signal is going to the base, and you see here you have some resistor capacitor arrangement also. So this part is nothing but it is actually again a low pass filter. So it is removing the all high frequency signal because you would like to operate your bass for the low frequency region. Effectively these resistor capacitors, these things are working, creating a low pass filter kind of thing. So that voltage is getting filtered again and it goes to this NPN transistor. Now from that NPN transistor, now here so some amount of amplification is going on here, and of course some filtering is happening, and from the emitter current you have in parallel you have your that bass adjustment knob. This is the bass adjustment knob, and from bass adjustment knob you have this resistor. This is the bass coil bass speaker resistance. Is kind of 8 ohm speaker is there. Okay, so you adjust this resistance and by rotating that knob of the bass adjuster, and you give a higher or lower voltage across this resistor. By adjusting this knob you can adjust the voltage of this subwoofer and accordingly the impact or sound of the subwoofer. So effectively the bass boosting section is nothing but a low pass filter which encompasses this section, and a class A amplifier using a NPN transistor, and you have this control knob. Okay, so I think you have got a good amount of idea about how this SBS A300 sound system works. So if you would like to repair your sound system or just simply understand how the circuit is working, so this video may have helped you. So if that is so you may like my video or subscribe my channel. So it actually took a good amount of time, rather lots of time, to understand the circuit by myself. So I have drawn this kind of schematic to understand things. So did a lots of analysis and then only I could understand what's happening here. Thank you. You were watching Devar Lab. Love you, friends.